We saw this theorem in the last video, right? Last video of this type. And we saw that there is something wrong with this theorem. And we offered a modification also, and we proved the modification. But that changes something. Namely, it changes the proof of the next corollary. Because there are other corollaries also. Luckily, they do not get affected. But this very first corollary actually gets affected. Unlike this statement of the theorem, the statement of the corollary is not false. But because the corollary uses in its proof the theorem, so now we need some kind of adjustment. So let's first see what the corollary says. It says this: if these vectors v1, v2, v3 up to vn in V have W as their linear span, and the first k vectors in this list of vectors are linearly independent. Then there exists a set of vectors of the form this. Let me write it as a set. Where those k vectors are present and possibly some other vectors are also present. Consisting of vectors from the list that is linearly independent. And still spans W. So what the corollary says is that we have a list of vectors in V. V is some vector space, and the linear span of these vectors is W. And the first k vectors in this list are linearly independent. This k may be 1, this k may be n also. Okay. All the possibilities are there, but k is a positive integer, that's for sure, and these are linearly independent. Then there exists a set of vectors of this form where all these extra vectors, if they are present, are also coming from those n vectors, okay, in that list, such that this set is linearly independent and it also spans W, that same space W that the original vectors span. The difference between this set and this list of vectors is that this list of vectors may not give you a linearly independent set. Okay, it may give you a dependent set. This set, however, is linearly independent and still spans that same subspace W. Now, the proof of the corollary starts like this. We don't have to go through the entire proof. We just need to modify it slightly so that our new modified theorem can be applied. Still, let me just write proof. This is what the first sentence essentially is. If the original vectors themselves are linearly independent, then we are done. Why? Well, because if the original vectors are linearly independent, then obviously you can take all the Vn's in this set. Does not matter what k is. You see, we are given that these vectors are linearly independent. Even if all the vectors are linearly independent, maybe k is less than n. Okay, we don't really know what k is. But still, if that is the case, if all of them are linearly independent, you consider actually all of them here. So they already span W, and now they form a linearly independent set also, and that's why we don't have to do anything else in this case, and we are done. What is the other possibility? Namely, that they are not linearly independent. And that's where we use that theorem. But what does the theorem say? The theorem says, in our modified form, it says that if we are given a list of non-zero vectors, that was one part of our modification. The vectors need to be non-zero. Then either they form a linearly independent set, or some Vk is a linear combination of the preceding vectors for some k greater than 1. Here, however, these need not necessarily be non-zero. 0 may be present in this list. The 0 vector may be present. Maybe it may also be present multiple times. That's also possible. I mean, this is not a set, this is a list, a finite sequence of vectors. Vectors may be repeated. So then how can we apply our modified theorem? For that, we need to do this trick. This is where we stop the proof for now and see something that is true in any vector space. So this is what we observe. Let V be a vector space and S be a subset of V. S is not necessarily a subspace or anything. Okay, S is just any subset of V. S may be empty also. S may be non-empty, and S may also be infinite, who knows. S is just any subset of V. This is our observation. We claim that the linear span of S difference the 0 vector. The linear span of this set is equal to the linear span of S. We are now going to prove this claim. What will this claim give us? It will give us the ability to replace the original vectors VI's, the original list of vectors VI, by another list where the 0 vector is not present. Do you see why? Because if S consists of those VI's, then L of S is your W. But in place of that list, you can also produce another list where the 0 vector is not present. On that list, however, we are able to use our modified theorem, the modified form of theorem 421. That's why we need this. Okay, so let's now establish this claim. Let us first consider the case where S is empty. If S is the empty set, then S difference 0 is also the empty set. And so, in this case, the two sets have the same linear span because they are just the same thing. That means our claim is true if S is empty. Now, let S be non-empty. Now we see the other case. Let S be non-empty. Since S difference 0 is after all a subset of S by a previous elementary result, the linear span of S difference 0 will also be a subset of the linear span of S. That means we just have to prove the reverse inclusion, namely that L of S is also a subset of this. For that, we take a vector in L of S. Our aim now is to prove that this X also belongs to this linear span. If this X is equal to 0, then obviously X belongs to this linear span. Why? Well, that's because regardless of what S set is, its linear span after all is a subspace of V and so should have the 0 vector. That's why in this case X belongs to this. So we can now further consider this, that let X be non-zero. Now where is X coming from? X is coming from the linear span of S and S is non-empty. So we have X as a linear combination of finitely many elements of S. This is happening because X is in L of S. So X is going to look like this: alpha 1 S1 plus alpha 2 S2, like that. Alpha something, say alpha MSM for some scalars F is the underlying field, of course, and some vectors coming from S. Not all zero. That not all zero part is going to be very important for us. We are not so much concerned about the scalars themselves here. The fact that the si's are coming from S is clear because x is coming from L of S. But all the si's are not equal to 0. Why? Because x is non-zero. If all the si's are 0, then of course x will be 0. Hence, so this means that even if some si's are really equal to the 0 vector, but still there are some si's which are not equal to 0 because x is non-zero. And that lets us now simply ignore those si's that are equal to 0. And that is why, let me write it and then you will understand. Hence, there exists a non-empty subset I1, I2 up to say Ik of the set of indices such that the S's corresponding to these indices are precisely the ones that are non-zero. Sij is not equal to 0 for all j of this type. That means what? We can now rewrite x in terms of these Sij's. Thus, x is equal to alpha I1 Si1 plus alpha I2 Si2, and like that it will go alpha Ik Sik. Alright. Now what can you say about this x? Note that each Sij present here is not just coming from S but is also additionally non-zero. So all the Sij's here belong to the set S difference 0, and that's why x belongs to the linear span of S difference 0. So we see that no matter what the case is, whether x is the 0 vector or a non-zero vector, it belongs to the linear span of S difference 0. Thus, Ls is also a subset of Ls difference 0, and that lets us write Ls equal to Ls difference 0. That was our claim. And then if you continue the proof of the corollary, this is what you just have to write. Because of this claim, we can assume without loss of generality that these are all non-zero. You can write that in words also, that these are all non-zero vectors. And that is why whenever they do not form a linearly independent set, you can apply the modified form of our theorem 4-1. And from that you get some v j, that's a linear combination of the preceding ones. And then the proof goes just as it goes in the text, okay, without any further modification. And it works. From there it works. So that's what I just had to say. There are many more little things like this. So I'll be making more videos on these things, and not just linear algebra. We will go to other areas as well. Even those areas which we have not touched so far. Okay. So with that, I just end this video. So see you in the next video. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.